Now let's just move on further towards the next theorem, which is actually called as the converse of the midpoint theorem, in which we have the theorem as a line drawn through the midpoint of one side of a triangle parallel to the another side. It bisects the third side. It bisects the third side. So first of all, we have this particular triangle. Let us suppose if I'm just taking the triangle as nothing but A, B and C, A, B and C, such that I'm taking this particular point as E, I'm taking this particular point as nothing but F, and I'm just joining these EF. So let us suppose if I'm just taking a given condition that a triangle ABC is given to us, in which E is the midpoint. E is the midpoint of AB. E is the midpoint of AB, and F is any point, on AC such that EF is parallel to BC. It is already given to us in the question that EF is parallel to BC. Now what we have to prove? We have to prove that AF is nothing but is equal to FC. Means we have to prove that F is nothing but the midpoint actually. Now let us suppose if I'm just again drawing a little bit of, or doing a little bit of construction over here in order to prove the theorem. So I'm just draw a line from C parallel to AB, So let us suppose if I'm just drawing this particular line parallel to AB, such that parallel to AB and extend, let us suppose if I'm saying and extend EF such that it intersects the line at any point D. So let us suppose if I'm just extending it as such that it will intersects this line at nothing but any point D. So this is nothing but the construction that I have taken over here, so let's just start the proof of this particular theorem. So first of all, since you can see over here that it is already given to us that EF is nothing but parallel to BC. So by theorem it is given to us that EF is parallel to BC. So it also implies ED is nothing but parallel to BC, because it is nothing but an extended line segment. If AF is parallel to BC, then obviously this ED is also parallel to this particular BC. Let us suppose if I am calling it as 1. Moreover, by construction, we know that CD is parallel to BA, which implies CD is parallel to BE. CD is parallel to BE. Since BE is nothing but a half of BA, so we can also say that if it is parallel to the whole line, then it is also parallel to a part of it. So it implies that CD is nothing but parallel to BE. So from this equation, from 1 and 2, what can we say? So from 1 and 2, we have ED is parallel to BC, and we have CD as parallel to BE, which implies both pairs are parallel, which implies BEDC is a parallelogram. It is nothing but a parallelogram, because in a parallelogram both pairs are parallel. So if both pairs are parallel, it implies that BEDC is nothing but a parallelogram. Now if it is a parallelogram, then we know that BE is nothing but is equal to CD. Since we know that the opposite sides are equal in parallelogram. So if BE is equal to CD, then it is also implies BE is equal to AE, since E is the midpoint. So what can we say from these two equations? Let us suppose if I am calling it as 3, I am calling it as 4. So from 3 and 4, we can say that CD is nothing but is equal to AE. CD is nothing but is equal to AE. That's what we are getting from here. CD is nothing but is equal to AE. Now furthermore, what can we say about the two triangles? So in triangle AEF and the triangle CDF, first of all, we know that AE is nothing but is equal to CD. It is already proven case. And furthermore, we know that angle AEF is equal to the angle CDF, because of the reason that since AB is parallel to CD and ED is a transversal, so they are forming up the alternate interior angles. So that's why they are actually equal to each other. Now furthermore, we can say that the angle AFE is equal to the angle CFD, because they are vertically opposite angles. So since if they are vertically opposite angles, so what can we say from these three conditions? That the triangle AEF is actually congruent to the triangle CDF by angle side congruence criteria. By AAS congruency criteria, we can say that the two triangles are congruent to each other, and if the two triangles are congruent to each other, then we can say that AF is nothing but is equal to FC by CPCT. If the two triangles are congruent, then their corresponding parts are also equal to each other. So AF is equal to FC is the thing that we have to prove. So hence it is proved that the line which is drawn through the midpoint of one side of a triangle is parallel to the another side, then it bisects the third side. So we have proved this particular converse of the midpoint theorem. Now after the midpoint theorem and the converse of the midpoint theorem, we can deduct a very special node. And what is that? Let us suppose if I am just drawing up the figure of the midpoint theorem and the converse of the midpoint theorem again. So let us suppose I am taking this particular triangle ABC, and I'm taking this as nothing but E, and I'm taking this as nothing but F, and I'm extending this as nothing but over here as in this manner, and we have taken this particular point as D. So many a times we just have proved that the triangle AEF is actually nothing but congruent to triangle AEF is actually congruent to triangle CFT. So in both of the theorems we have proved this concept that the two triangles are actually congruent to each other, and if they are congruent to each other, then we definitely know that EF is nothing but is equal to FD. It implies EF is nothing but is equal to FD, which implies that EF is nothing but actually nothing but half of ED. It is half of ED, and in the converse of the midpoint theorem, we have proved that EBCD is nothing but a parallelogram, which implies that BC is nothing but is equal to AD. If we have BCDE as a parallelogram, if we have taken it as a parallelogram, then BC is equal to ED. It implies that EF is nothing but half of BC. EF is nothing but half of BC, which is a really an important concept over here, because it will definitely help us to prove many such questions which are related with the converse of the midpoint theorem and the midpoint theorem. So this is a very special note. Then since in the midpoint theorem we have taken taken the EF as parallel to the BC, then EF is nothing but a half of ED, as we have taken, which is nothing but half of BC. So always remember, whenever we are just talking about this particular EF, which is nothing but a line segment that we are getting after joining the two midpoints of a particular triangle, which is parallel to the third side, then it is not only parallel to the third side, but it is half of the third side, means EF is nothing but half of the third side. So this is nothing but an important result which is related with the converse of the midpoint theorem and the midpoint theorem.